Metal additive manufacturing, post-processing of printed parts. This video has been produced in projects I2P, from idea to printing of metal products and hybrid, efficient applications using multi-method production. Both projects have been funded by the European Union. Did you know that AM processes are divided into 7 categories, and all of these have one or more commercial metal AM methods? Over 18 different metal additive manufacturing processes are known. However, laser powder bed fusion is by far the predominant metal AM method at present, so this presentation will focus on the post-treatments used with the laser powder bed fusion method. Of course, all post-processing methods are independent processes, so they can be used with other methods as well. The figure shows a typical work step for additive manufacturing. Please note that the post-processing steps may not always be in the order shown. It is also worth of noting that when the platform has different parts, depending on the requirements set for them and the technical details, the work steps for the post-processing of each part may be different. Taking the post-processing into account already begins in the design of the part. The functional requirements of the part and its connection to another structure may create the need for good surface quality or for shapes for which the accuracy of 3D printing is not capable. These include, for example, sealing surfaces and tolerance fittings as well as threads. In the geometry of the part, downskin surfaces may need a support structure. This can be avoided either by designing the surfaces more vertically or by printing the piece in a position that no support structures are required for these surfaces. The general surface roughness tolerance of the part should be set loose and set the more precise surface roughness only where it is really needed. If the part has areas that need to be machined, it must be possible to fix the part for machining. To do this, you may have to design mounting points or even separate mounting parts for the part. The same situation exists if post-processing of a part is automated and robots are used to process the part. The place where the robot can grab the part must be known in advance. Minimizing the need of post-processing example. This part is designed to be easy to print, and requires only minimal post-processing. The part designer has designed the part to present some of the most significant advantages of the laser powder bed fusion method. That is, it is possible to implement very complex internal forms. Structures can be made that would require several parts by other manufacturing methods. That is, the assembly can be compacted into one part. Also, different functionalities can be implemented in the same part. There is, for example, cooling channels, a nozzle structure, and the operation of the structure as part of the frame structure. There is no need for support structures. If a part is removed from the platform using wire edam, its bottom also becomes smooth and it does not need any other post-processing. After printing is complete, any unused powder will be removed from the printing chamber. Here, a spatula, a brush, a pressurized gas, and a vacuum cleaner will be used. Such a powder, which is recovered in a shielding gas atmosphere, can be recycled by sieving the powder. The rest of the powder is treated as waste. After the building platform and parts are cleaned at powder, platform will be removed from the machine. Depending on the situation, heat treatments of metal printed parts can have several purposes. The properties of metals can be affected by heat treatments quite a lot. Metal heat treatments include, among others, stress relief annealing, normalizing, aging, quenching, and tempering. The first possibility for heat treatment is when the print platform with parts have been removed from the printer. In this case, it is usually a case of stress relief annealing, but the heat treatment also has another favorable effect, as it causes the solidification structure created in 3D printing to recover. Some typical heat treatment situation. Heat treatment after build removal to help relieve residual stresses and recover the solidification structure. Heat treatment before machining to annealing the material, and reduce hardness. This is sometimes needed because due to rapid cooling in most metal printing processes, the material can be in a highly hardened state that is difficult to machine. HT after machining to achieve final hardness requirements, and desired metallurgy phases and grain structure. Furnace sintering, required for powder binder processes after binder removal. It can result in a lot of shrinkage and drift in geometry. This must be compensated for upstream at the design stage. Opto-isostatic pressing, HIP, often used by powder processes after part separation to decrease porosity and further relieve stresses. The parts are typically removed from the building platform by sawing, most commonly with a bandsaw. Wire EDM is also often used because of its good sawing surface quality. Of course, the parts can be removed from the platform by hand tools or by machining. It is noted that in some cases, the parts may be in many layers and attached to each other. To remove the parts, a clearance is left between the platform and the parts. It is typically about 3 mm for a bandsaw, depending of course on the saw used. When using wire EDM, the working margin is about 0.3 mm, depending, of course, on the hardware used and the thickness of the wire. The advantage of the wire EDM method is a good surface quality. The sawing surface is often good as it is. The method can also be used to saw the shape. In some cases the parts no longer need any other finishing. The downside of the wire EDM is its slowness. Either hand tools or machining have traditionally been used to remove the support structures of the pieces. Various hand tools such as pliers and cutting nippers are used for manual removal of support structures. Of course, power tools and pneumatic tools such as mini and micro grinders, die grinders are also used. Generally, manual removal of subsidies is considered laborious, but when supports are designed to be easily removed, it is understood that manual removal may still be the fastest method of removing subsidies. If the parts contain precise geometrical features that are easiest to make by machining, it is advisable to design the supporting structures so that they can also be removed by machining at the same time. Non-mechanical methods can also be used to remove the support structures. For example, etching and electrolytic polishing can be used in combination with mechanical methods. An example I will go through later is the hertization process, which utilizes combination of electrochemical pulse methods, hydrodynamic flow and particle-assisted chemical removal and surface treatment. Machining can be used to remove support structures, to make precise shapes, to achieve good surface quality, and to make special shapes such as threads. Machining can be turning, drilling or milling. Of course, the part can be subjected to all these and also other measures classified as machining. Features of machining include tolerated holes, threads as well as precise shapes and surfaces. When it is known that we have machinable shapes in the part, then it is worth considering the mounting of the part in machining at the part design stage. This may mean that the part includes shapes from which it can be mounted to a machine, or special fixture parts, possibly 3D printable, can be designed for the part for machining. Surface treatment can have several purposes. Increasing geometric accuracy. Elimination of surface defects and traces of supporting structures. Improving appearance. Modification of surface friction properties. Improving connectivity. Improving corrosion resistance. Improving chemical resistance. Improving wear resistance. Changing the surface hardness and changing the electrical conductivity. Surface treatment methods can be roughly divided into two main categories: removing and shaping methods as well as adding and modifying methods. Often these methods are used sequentially, that is first, for example, sandblasting and then painting. In removal and shaping methods, material is removed from a part, and at the same time the surface layer of the part is formed. These methods include mechanical surface treatment methods as well as various chemical, electrochemical, and chemical-mechanical methods. The most common mechanical surface treatment methods are sandblasting and grinding, and the most common mass finishing methods are drum polishing and vibratory polishing. Peening and its various variations are also very common methods. In these processes, the surface of the metal is modified to improve its material properties. Local modification on the surface of the metal is intended to cause compressive stresses, which also reduce any tensile stresses on the surface. Peening also shapes the metal surface. When peening shapes the surface and also changes the material properties, then it actually belongs to both groups. In adding and modifying methods, a coating is deposited on the surface of a part, or the microstructure of the surface layer of the part is altered either chemically or mechanically. This gives the desired properties to the surface, such as appearance, electrical conductivity, corrosion resistance, wear resistance, and so on. The most common of these methods are painting, as well as other coating methods and surface hardening methods. And, as mentioned earlier, peening. The hardware is very similar in the methods of abrasive blasting, glass bead blasting, shot peening, and microblasting. Safety cabinet and nozzle with which the working medium is blown into the workpiece. Surface mechanical attrition treatment, SMART, improves mechanical properties of metallic materials through the formation of nanocrystallites at their surface layer. It also modifies the morphology and roughness of the work surface. Attached are the results of bending fatigue tests with AZ360mm material with different treatments. The results show that the surface work hardening and the compressive stress state obtained on the surface have improved the bending fatigue resistance of the test specimens. Tumbling is a mass finishing technique for smoothing and polishing a rough surface for relatively small parts. The drum blast machines are used to clean castings, and are suitable for coarser cleaning of AM parts. Hertization, from Rena Technologies Germany, is method for automatic post-processing of 3D printed metal parts. Three-phase method is based on a combination of electrochemical pulse methods, hydrodynamic flow, and particle-assisted chemical removal and surface treatment. In first step, support structures are removed. Surface roughness will reduce to Ra 10 micrometers. In second step, surface roughness will reduce to Ra value 2 micrometers. Optional third step is high polishing phase. Surface roughness will reduce to Ra 0.5 micrometers. As a brief summary, it could be noted that the technical requirements, design and work planning of a part greatly influence the need for post-processing of the part. The part should be designed so that the need for post-processing is kept to a minimum. It is also good to be aware of what post-treatment possibilities are in use. In practice, this means that the shape is designed to minimize the need for support structures. If the part has exact features that require machining, the attachment of the part during machining should be considered at the design stage. If possible, the overall tolerance for surface roughness should be kept high. The post-processing technology currently in use is very much based on craftsmanship and machining. However, in Finland, for example, also tumble finishing equipment are used. In the future, we can assume that automated processes such as Rena hertization will become more common. And here was our presentation. Thanks for your attention.